Log on, tune in, find out. Another good idea from Cambridge.
To have a good recording. Once it was too loud, once it was not loud enough. Okay, now they seem to be happy after the third time. Right, so it's a pleasure to introduce our next speaker, Thomas Lam, who will speak about total positivity in loop groups.
Thank you. Thank you for the opportunity to speak here. So I'm talking about total positivity in loop groups. And the talk is based on joint work with Pavlo Piliaski. So let me first tell you give you the definition. So first, a matrix, a usual, I guess the matrix, a real matrix, X is totally non-negative. If and only if all the minors of X are non-negative. So you take any minor, any square submatrix, and you take its determinant. And so I want to try to apply this definition to a matrix with polynomial or Laurent series entries. So I'm going to take a matrix X of T, and it's going to be the loop group I want to consider is the formal algebraic loop group with real coefficients. So n by n matrices with coefficients in this field. This is the field of formal Laurent series. So a typical matrix entry looks like some. So you start at some finite negative integer, or well, maybe positive, and then you go up to infinity. So that's what the entries look like, and it has to be non-singular. And so I want to now say, to now define what it means for a matrix like this to be totally non-negative. And so I'll give an example. So here n is equal to 2. And so I'm not going to write down power series entries. I'm just going to write down polynomial entries. So here's such a matrix, and you can calculate its determinant to see that it's non-singular. So I can't apply I can't obviously apply this definition to this matrix, but I'm going to replace it with another matrix and apply the definition. So what I'm going to do is I'm going to take I'll start by taking the constant coefficient of this matrix and putting it in a block. So constant coefficient is 2, 1, 5, 0. And I'll repeat this block along what's the main diagonal of this infinite matrix. And then in the next diagonal, I'm going to put the coefficient of t. 1, 0, 0, 5. And in the next one, the coefficient of t squared. 0 minus 1, 0. And t cubed. And in these entries, the coefficient of t inverse. So and 0 is down here. Okay, so I'm going to say this is totally non-negative if and only if this guy over here is totally non-negative. And so this is a very standard way to view an element of a loop group. Okay, so what do I want to do with these matrices? The main thing I want to talk about today about totally non-negative elements is to try to factorize them into simple factors. So,
but it simply means that you take standard basis t to the n and look how matrix acts.
right. Yeah, so for example, you could look at, so these are, say, matrix coefficients in the Fock space. So I want to try to factorize these matrices into simple factors. And so why should one want to try to do this? Why should one want to try to factorize these matrices? I'm going to give you two special cases of this theory and tell you what the relationship is with representation theory. So first, the finite case, and the second case is the n equals 1 case. And both of them have known relationships with representation theory. So the finite case, so x of t is a constant matrix. So it doesn't depend on t. So it's just an n by n non-singular matrix with real coefficients, and then this is the usual definition of total non-negativity. So I'm only going to talk about the type A case in my talk, but so Lustig in this case has a generalization of. So whenever I write some kind of matrices, the totally non-negative part is written like this. To g greater than 0 for other reductive groups. And let me tell you, so one way, well, let me tell you a theorem of Lustig. So let's write U finite, because later on I'll have the loop group version, to be the upper triangular unipotent matrices. And so I'll have something like U finite greater than or equal to 0. So let me tell you about this part, which is kind of the easiest set of totally non-negative matrices to analyze. So first statement, which is that it's the semigroup. Yes. Semigroup generated by the one parameter subgroups, which I'll write EI of A with positive parameters.
By U positive, you mean intersection of U with G positive.
Right. So I'll just take upper triangular matrices with ones on the diagonal, such that this condition is satisfied. Yeah. And it's exactly the intersection with GLNR greater than or equal to 0. So put zeros everywhere except in the ith row and I plus 1 column, put an A, and ask that A is greater than or equal to 0. And the semigroup generated by this is U greater than or equal to 0. So this is Whitney's theorem. And go over here. And the second part of the theorem tells you how it interacts with the Bruhat decomposition. So just this set of matrices, if you is a disjoint union of pieces labeled by permutations u sub w, I guess, going to 0, and each u sub w then 0 is a set of matrices of this form. L where and w. So pick a reduced expression. Pick a reduced expression for a permutation and multiply these corresponding one-parameter subgroups together, and then you're going to get a piece which is exactly the intersection of this with the Bruhat decomposition. And in addition, this will be a parametrization. So this thing. Strictly greater than 0. So in this case, I want it to be strictly greater than 0 here. So otherwise it won't be a disjoint union. And each of these pieces is homeomorphic to R strictly greater than 0 to the length of W. And so part of the claim is that this piece will not depend on the choice of the reduced expression. So. And this is the framework in which it's generalized to other reductive groups. So I won't talk much about that. So one way it's related to other things Lustig was interested in is that when you ask the question of what happens if you change reduced words, it corresponds to a problem Lustig studied with canonical bases. So if you take two reduced words, so I'll write shorthand EI tilde A tilde for this expression. So if you have two reduced words I and J for the same permutation, and then then you're going to get different parameters. So there's some A and there's some B. And A tilde to B tilde will be related by some transformations. And the transformations are rational rational subtraction-free expressions. And it turns out that these kinds of expressions, when you reparameterize a particular matrix in this form, exactly correspond to Lustig's different parameterizations of the canonical basis when you change the reduced word for the longest element. So these parameterizations. Canonical basis for, I guess, UQ n plus when changed. So Lustig parameterized his canonical basis by lists of non-negative integers, and they correspond to these expressions when you change. So here these are positive real numbers, and in Lustig's parameterizations they're integers. What you have to do is you have to change from this semigroup, from this semifield to the tropical semifield. 0. Okay, so I won't go further into this, but there's an analogy which led Lustig to investigate this in the first place. And so this direction has been has been sort of understood more from the point of view of cluster algebras, but I won't talk much about that. So factorizing these matrices is not is a reasonable thing to do, is what I'm trying to convince you. So there's another sort of more, I think, a more robust connection with representation theory in the case n equals 1. So n equals 1 is GL1 R double brackets T greater than or equal to 0. So what are these things? I'm only going to focus on the part which is U greater than or equal to 0. So again, these are the ones where I take the matrix and write it in this form. It looks unipotent. Okay, so these things are one by one matrices whose coefficient is a formal Laurent series. The fact that it's upper triangular means that it's actually a power series. So it consists of elements which look like this. The AIs are real numbers, and what's the condition for it to be plus? There's some condition for it to be totally non-negative. What's the condition? So you take this power series and you replace it by an infinite periodic matrix according to that strategy, and you get something like this. And the condition that this power series is totally non-negative is like, so one condition is that every entry is greater than or equal to 0, but you also need to check determinants. So for example, you want to check A1 squared is minus A2 is greater than 0, and you want like A2 squared minus A1, A3 is greater than or equal to 0. And there's lots of equations. So one interesting thing about this is that these equations are semi-algebraic, they're polynomials. But when you try to solve the problem, you go into complex analysis. So what's the solution to this problem? So I want to classify all power series looking like this, satisfying all of these inequalities. So the theorem, so this is Adray. It's called the Adray-Thomas theorem. Says that, so this A of t is totally non-negative if and only if it's of the following form. Where all these parameters are non-negative, and this converges. And the condition that this converges is that the sum of all the parameters is finite. Okay, so there's kind of a surprise. We started with what looks like an completely algebraic thing, but actually the solutions to this problem is actually a meromorphic function. So first, every totally non-negative power series is actually a meromorphic function, and it's basically it's nearly all the information is in where its poles and its zeros are. So its zeros are negative real numbers, and its poles are positive real numbers, and there's a very simple exponential factor. So what good is this classification? So also there's this expression is unique. So given such a given such a thing, which is called a totally positive function, it uniquely is determined by its poles and zeros, and you can extract all the information out. So I want to think of this theorem as an analogy of the kind of factorizations done up there, where I took a matrix and I factorized it into these elements in one parameter subgroups. I want to think about these factors here, these linear factors and their inverses as also like that. And the parameters alpha I and beta I now play the role of the AIs. Okay, so Andre studied this sort of just as a cute analysis problem. But Thomas studied this when he was studying the representation theory of the infinite symmetric group. So what's the theorem? So first I'm going to say A of t is normalized if A1 equals 1. So I'm just going to restrict myself to those solutions to this problem where A1 is equal to 1. The reason why I might want to do this is that the space becomes compact. But anyway, so the theorem says normalized A of t, totally non-negative, in bijection with characters of S infinity. So this is Thomas' theorem. So what's S infinity? So S infinity is the infinite symmetric groups. It's just the union. It's just a union of all the symmetric groups embedded in each other in the obvious way. What's a character of S infinity? So a character is a function chi from S infinity to the complex numbers, and it has to satisfy a bunch of properties which I won't go through in detail. So it's a little bit different to characters for a finite group. So the sort of official definition of a character is that it has to satisfy four adjectives: normalized, extremal, central, and positive definite. So normalized is a condition you usually don't consider for usual finite groups. So that says the value at the identity is 1. Extremal corresponds to a character being irreducible, essentially. Central says it's a class function. And positive definite says that it's actually is a representation rather than a virtual one. So there are these four adjectives which make a function into a character. And actually all characters take values not in, they end up taking values which are in the reals rather than the complexes. So maybe this is kind of still a bit vague. You don't know really how to compare this to what you know about the finite symmetric groups. So let me be a little bit more precise how to get a character of the infinite symmetric group from characters of finite symmetric groups. So to get a character of the infinite symmetric group, you have to say what the value on any element of the symmetric group, infinite symmetric group is, which is you have to tell me what the value on every so every element in the infinite symmetric group lies in some finite symmetric group. So one way to get a function of finite symmetric groups is to take characters of finite symmetric groups. So so from this point of view, the theorem is due to Kirov and Vershik. So the first part of the theorem says that every character on the infinite symmetric group can be obtained by taking a limit of characters of the normalized characters of the finite symmetric group. So every character is a limit of characters chi lambda 1 from S1 C, and then chi lambda 2. and these are irreducible characters of labeled by partitions, except that they're meant to be normalized. So, so you have to divide by their value at the identity. So it's a normalized irreducible character. So given an element of the infinite symmetric group, it will eventually one of these functions will be, you can evaluate at that element of the infinite symmetric group, and afterwards all the other ones you can evaluate at that element, and that will give you a list of numbers, and then it will converge to something, which will be the value of the character. So every character, so obviously not every list like this will converge to something. Most of them, well, actually, if you randomly pick partitions which kind of grow by adding boxes, then it will actually converge to some limit. But so every character is a limit, so it's determined by a sequence of partitions. So that's one way you can think about characters of the infinite symmetric group. How do I put this in the context of?
It's a pointwise limit.
Yes, it's a pointwise limit. So for every element of the infinite symmetric group, its value converges to some. I mean, it will be a real number rather than complex.
But not all pointwise.
Sorry.
All pointwise limits give a character, or you take overs.
I'm not sure. So for every element here, the pointwise limit will converge. That's part of the
If you have a sequence which pointwise converges, it gives you.
I think yes. I think that is true. So if you have a sequence of normalized irreducible characters which converge to something, then what it converges to is a character. I believe that's true. I'll have to think about it more though. So here's how you can think about characters of the infinite symmetric group if you know about the finite symmetric group. And so where do the totally non-negative matrices come in? And as I was saying, the thing I want to talk about is how to factorize these matrices. So the second part of the theorem tells you what these parameters mean in terms of representation theory. So after I've written my chi in terms of as a limit, you can obtain these parameters by looking at how these partitions grow. So every normalized irreducible character is labeled by a partition, and now you want to ask how these partitions grow. And so there's a formula for what the beta I is. So to obtain the pose of this corresponding totally non-negative function, what you have to do is you have to take your partitions, look at the ith row of your partition, and normalize it, and then take a limit. And this, so it tells you roughly, beta I tells you roughly how fast the ith row of your partitions are growing as you're taking this limit. And so alpha I is columns instead of rows. Yeah. And gamma is determined by alpha I and beta I by the normalization condition. So that parameter.
But what does that mean? You take the column as a vector, divide it by n.
So you've got a list of partitions, lambda 1, lambda 2, lambda 3, and then you look at the you look at the third row of this partition, and that will be some length, and the third row of this one, and the third row of this one, and it'll be getting bigger and bigger because these partitions are getting bigger and bigger.
It's length of the row.
Yes, the length of the row, right? Okay. Yeah. So this is the length of that row divided by n, and it will approach a limit. So the fact that the pointwise limits exist imply that these limits will exist. So basically these factorization parameters tell you asymptotic information about the characters. So one way I want to think about it is.
And what is gamma?
Sorry?
What is gamma?
Gamma is determined by alpha I and beta I by by the normalization condition that was there. So gamma plus sum over alpha I, sum over beta I is equal to 1. In fact, if you randomly pick partitions, you get something which might be called the regular character of the infinite symmetric group, and then all the alphas and betas will be 0, and the gamma will be 1. So if you randomly pick partitions and take this limit, you most likely get gamma equals 1 and everything else is 0. But you get that with probability 1. So one way I want to think about this is you have characters of S infinity, and they correspond to certain meromorphic functions, certain meromorphic functions from complexes into GL1. And so I guess the point of my talk is to ask what happens when you replace GL1 here by another group, in particular GLN.
So why do you write complex GL1? I mean, they're just meromorphic functions, right? I mean, they're not invertible. I mean, they have zeros, right?
Yeah, they have zeros. So they have poles.
So you just at this point you just prefer to think about the images landing in GL1. I mean, it's not. Is there a way to explain why somehow? I mean, GL1 is basically C star. Why do you think about it as a C star is not another C, the target of the function?
Speaking of A of T, I think.
Yes.
I mean, that A of T is in loop GL1.
Yes, but I thought.
Yeah, well, I'm looking at this guy to begin with. So these guys were originally formal loops into GL1, and they turn out to actually be meromorphic loops. Though maybe that's not a significant.
Oh, I see.
So this would be formal loops into GL1, but now, for now I want to think about them as meromorphic loops with some additional positivity conditions. So actually, I don't know what goes here, but I think there should be something interesting there. But what I'm going to tell you a bit about is how to try to tackle these problems of factorization. So to kind of simultaneously generalize factorizations like this and factorizations like that, and there's some interesting combinatorics, I think. Yeah. So let me not rub this off yet. So now I want to look at n greater than or equal to 1. So I want to look at this so upper unipotent inside GLN. So those kinds of matrices. And now, so I want to take an element here and try to factorize it, and try to interpret a little bit what the parameters mean. So let me first tell you a theorem which looks a little bit like this. So X is a matrix inside there. There is a unique factorization AYB, which morally is meant to be thought of as some factorization like that, where y is entire and y inverse is entire. A is a product of factors which look like poles. I'll say a bit more about this. And B is a product of, possibly an infinite product of factors which look like zeros. So I haven't told you yet what these matrices Ni and Mi are, but these Ni and Mi, so the Ni are factors which are matrices which correspond somehow to these linear factors here, and the Mi are factors which correspond to that. And the middle part is something which looks like an exponential. So it's an entire, so what does it mean for a matrix to be entire? So every matrix entry is entire, and every matrix entry of the inverse matrix is entire. So if it's a 1-by-1 matrix, it's the exponential of something. Something entire. Okay, so what are these? Matrices? So I'll draw you a picture of Mi, which is the matrix which is meant to look like a 0, and I'll draw you in the infinite. I'll draw this matrix in the infinite form for n equals 2. So Mi will depend on two parameters, A and B. And what you do is you just put A and B along the diagonal immediately above the main diagonal. Okay, so this matrix can't be written in terms of this matrix can't be written in terms of one-parameter subgroups. So it's just not in the group generated by the one-parameter subgroups with one-parameter subgroups for the roots. And so in the case, if you do this but it's n equals 1, then you get the matrix which is 1, 1, 1, 1, 1, A, and that's exactly the matrix which corresponds to 1 plus alpha it. So that matrix is looking like this, but which depend on n parameters rather than 1 parameters. And after you factor out infinitely many of these pieces, and you also do the same thing for poles, you're going to get left with something which is entire. And this factorization is an analog of this, except the main deficiency of this theorem is that I haven't specified what's allowed in the middle. I should also say that A and B are both greater than or equal to 0.
What about Ni's?
So Ni's are a little bit more complicated. Like this. So they roughly look like the inverse of the MIs, except that the inverse of the MI is not going to be totally negative. So they look like the inverse, but there's a slight modification to make them positive. So the n of AB looks like so directly above the diagonal it looks the same. In the next entry it's all ABs. Oops. And in the entry above it oscillates between A squared B and B squared A. Okay. And all the entries are non-zero as you go up.
And A and B are first.
Sorry?
A and B are positive or?
A and B are, well, let's say they're positive. Right. So in the special case, in the special case that one of the A or the B becomes 0, you get something which is which lies in a one-parameter subgroup. So it'll look like a Chevrolet generator. So if I took M A comma 0, then it'll look something like, and 1, 1, 1, 1 A. It'll look something like this, and this is what I would call E1 of A. And M of 0 comma A is what I would call E0 of A. So in fact, that's what I want to talk about now. Is so these matrices are a little bit different. So I was trying to talk about this analogy between these Chevrolet generators and also these factors here. But
Between N and B goes first, or it is infinite. So
It's infinite, so there are non-zero entries all the way. Right. So there's a kind of significant difference between the E0A and the M of A comma B, in that the M of A comma B it's got zeros. The N of A comma B has poles, as in the matrix entries of these things. But if you take the Chevrolet generators, then they don't. They're functions which are entire. So these E0A and E1 of A actually lie in the Y part, which is the reason why this theorem is more complicated than in the n equals 1 case. So in the n equals 1 case, after you've gotten rid of all your poles and zeros, you're left with an entire function, and then you prove that the entire function is an exponential of a linear factor. In this n greater than or equal to 1 case, the stuff inside Y is complicated, and that's the part I like to talk about, and I want to sort of focus on some explicit sort of Coxeter theoretic combinatorics which comes up when you try to study what's going on in the Y part. So
if you write these matrices in terms of 2 by 2 Lorentz series, then they're probably quite simple.
They're not that complicated. So they look like M of A comma B looks like this, and N of A comma B is the inverse of this, but you change the A and B so that all the entries are positive. That's all you have to do. Yeah, but this matrix has a 0 here because this function here, as a function of t, it's got a 0.
Sorry, I didn't understand the last. So you said that if t is equal to 0, now you still get you get a matrix which is still invertible. So why is it bad?
So its determinant is its
so
determinant is 1 minus ABT, which has a 0 at t is equal to 1 over
not
AB.
equal to 0, but some other t.
Right. So for t equals 1 over AB, this will not be an invertible matrix. So this is not an entire. Sorry. Its inverse won't be an entire loop from C to GL2. So I want to focus on a subset of Y. On Y, which contains sort of the affine simple one-parameter subgroups. Sort of these EI of A, where A is greater than 0 and I is I is one of the nodes of the affine Dinkin diagram. Okay, and if we just look at finite products of these things, it's actually kind of boring. You recover a version of Lustig's theorem. So I don't want to talk about that, and I want to just talk about infinite products of these things. So let's look at matrices. EI1, so of A1, A2, and it goes on forever. So this is an infinite product, and most of the time it doesn't converge to an actual matrix, but this converges if the sum over AI is less than infinity. So all my AIs are positive. So this is an absolute convergence. And what kind of indices do I want to put here? So in the finite case, we put a reduced word of a permutation. Here I've got an infinite list. I want them to be an infinite reduced word. So I1. You can also consider it for for infinite words which aren't reduced, but just for simplicity, I want to look at infinite reduced words. And what's an infinite reduced word? An infinite reduced word is an infinite word in these letters, such that every finite initial subword is reduced. Implies all finite initial subwords are reduced. So you can think about this as taking a chain in the weak order of the affine symmetric group and starting from the identity and going up and always heading up. Okay. So I want to look at matrices looking like this, and I want to say what these matrices have to do with sort of the combinatorics of infinite words of this form. So as I said, if you actually just look at finite products, then you get some version of Lustig's theorem where the affine Weil group replaces the Weil group, and not much new going on. So I'm going to write omega for the set of these matrices. This is not the whole of Y. This is just a very small part of Y, but is infinite reduced word, and the AI's are positive such that the sum is bounded. So I want to look at matrices like this. You have some matrices. This will be a subset of U to 0, and it will consist. You can prove that these matrices will always be entire and the inverses are entire. Okay. So in the finite case, when we so if I tilde is I tilde and J tilde are reduced words for some W, so for some finite permutation, then you can always rewrite some product of this form into some product which corresponds to a different reduced word. And so what's the analogous thing when you do infinite reduced words? It turns out to be rather more complicated. I want to give you an example of, so whenever you have two reduced words for the same permutation, you can always change one to the other by some local moves, some braid moves. In type A, you only need commutations and braid moves. More interesting things happen when you look at the infinite reduced words. You get things called braid limits. So I want to try to say what it means for two infinite reduced words to be the infinite reduced to be like equivalent or braid equivalent in some sense. And so let's start. Let me do an example. N equals 3. So this is the affine symmetric group S3 tilde. Dinkin diagram looks like 0, 1, 2. And I'm going to take the following infinite word. So here's an infinite word. It starts 1 and it goes 0, 1, 2, 0, 1, 2, 0, 1, 2 forever. It might not be obvious but it's true that this word is actually reduced. This is an infinite reduced. If you take any initial chunk of it, this will be a reduced word in the affine symmetric group. Now what I want to do to it is to now apply some braid moves to this infinite word. So I'm going to start off by applying a braid move to 1, 0, 1. So all the generators are adjacent, so they all get their own braid moves. So after applying a braid move to 1, 0, 1, I'll get 0, 1, 0. And I can apply a braid move here, 0, 2, 0. And I'm going to keep doing this. 0, 1. And I'll apply it to 2, 1, 2. And I'll get and the next braid move I can do is at 1, 0, 1. Okay, but I think you can already see the pattern. What you get afterwards is something which starts like 0, 1, 2, 0, 1, 2. And so if you do this process infinitely many times, you get another word which is also reduced, and it's this word. 0, 1, 2, 0, 1, 2, 0, 1, 2. So I call this operation a braid limit. So going from this word to this word. So the main thing which is different to the finite case is that you can't go back. After you've started with this infinite word and you've done infinitely many braid moves and gone here, you're stuck here and you can't actually go anywhere. There are no braid moves to be done over there. Okay, so braid equivalence is a little bit more tricky when you do infinite words. So I'll write for this whole operation, I'll write this just an arrow to mean that there's a braid limit, but then there's no braid limit back. Okay, so these words are not equivalent in this sense. So what's the theorem which relates this process to the infinite products of matrices? So this is a purely combinatorial process which you can do for any Coxeter group, but is related to these matrices. So if you've got a braid limit, then you can rewrite ei tilde of a tilde in terms of the ej tildes. Right, x can be and ej tilde of some other of b tilde. So maybe this seems obvious because you can perform some local manipulations. Every time you've got a braid move, you can perform some local manipulations on the level of the one-parameter subgroup. So what are the local ei of b? So in terms of matrices, whenever you've got two simple generators which commute, this is what happens with the one-parameter subgroups. And if you have and for the braid move, you have something which looks like this. So if you do an infinite sequence of these moves, you can do it on the level of matrices. But it turns out that this theorem is actually hard to prove because when you do an infinite sequence of moves, on the level of matrices, you have to prove that something converges. And it turns out that this theorem currently stated in this form isn't true for other Cox-Moody groups. So it's something special for affine groups. So if you take sort of the simple one-parameter subgroups and you do these operations, it's possible that these matrices aren't equal. So these elements of the Cox-Moody groups aren't equal. Though there's a variation which is more complicated than braid limits, which allow you to do infinitely many manipulations. Okay. So nearly out of time, but let me just tell you some more combinatorics about these braid limits.
I didn't understand what the statement of the theorem. So suppose that you obtain this braid limit, ej of b from ei of a.
Right.
What do you claim?
So this is a purely combinatorial thing on the level of infinite words. This word can be rewritten from this word by doing infinitely many braid moves. If that's true, then the corresponding matrix for every A can be rewritten in this factorization, has a different factorization for some other B.
Yeah.
That's the claim.
That B can be computed from this.
B is difficult to compute. So it can be done, but I mean, the answer is a limit. So the transition formula from the A's to B's is a complicated formula. So it's a very complicated expression. Well, I guess it's still a rational for every entry B I in here. It's still a rational expression in terms of the AIs. Except that as you go further out, the rational expressions get very complicated. So the degree doesn't get bounded or anything like that. So let me consider the set of all infinite reduced words and put a partial order on. So I'll say I is greater than equal to j if they exist a braid limit. And this is not yet a partial order. It's only a pre-order because there are some words where you can go somewhere and you can also come back. So there are equivalence classes under this order. So this is a pre-order. And so let me pretty much out of time. So this so the equivalence classes of this pre-order are the braid equivalent infinite reduced words, and so this, and after you factor out by the equivalence, you get some poset, and this poset lives above the weak order of the affine symmetric group. And actually, this poset is more infinite than a usual weak order in the sense that it has there are intervals in this order which themselves are infinite, while in your usual Brouhahn weak orders, you don't have this issue. Okay. However, this partial order has minimums. So minimal elements in this partial order are exactly the infinite Coxeter element. So what's an infinite Coxeter element? That's what you take a Coxeter element, you multiply it by itself infinitely many times, and this is an example. So this is a Coxeter element multiplied by itself infinitely times. So e.g., for n equals 3, the minimal elements in this order are one of the following things. Okay. As a corollary of this, every matrix X which can be written in this form can also be written in a form where the J tilde here is periodic, like given by a Coxeter element.
What do you mean by this? So you take 0, 1 to repeat infinitely many times?
And well, part of the theorem says 0, 1 to repeat it infinitely many times is a reduced word.
But after that you do it again? You do it 6 times?
Oh, sorry. I'm saying that this is a minimal element. This is another minimal element.
Okay.
Sorry. Yeah, that's what I meant. So this poset has 6 in the S3 tilde case has 6 minimal elements, and these are the minimal elements. Yeah, stop here. Thank you.
Thank you very much. Are there questions, comments?
So when you take the corresponding orders, then you get some collapses because it could be that different elements are greater than each other.
Right. So
then you put them to be equal.
Yes. So this is only a pre-order, and you get a partial order from this by factoring out by the equivalence classes.
So
that means that every one of these positive things has a canonical expression. Yeah, it corresponds to exactly one minimal.
No, that's not true. You can be above more than one of these things, and so it can have. So we have studied certain canonical factorizations, but you don't get canonical factorizations by rewriting them in this form. I believe that there's a canonical factorization if you try to write it as high as possible in this partial order, rather than try to write it as low as possible. Yeah. So you can have an x which can be written in this form and also in this form.
Further questions?